Now we come to the case of RE load. RE load. Resistor and some battery source. It could be, DC motor also. Now we will draw the circuit. RE load means what? Load is R and E. This is connected to source through some control device. This you can ground it. Now, for beginning this one, just I will tell you some basics. For this, we got to refer to our chapter on basics, but still, I am recalling for your convenience. The power absorbed by battery, okay, by battery or the EMF source. It is E into the average current flowing through it. For this you refer to our chapter on basics. Okay. Similarly, power absorbed in resistor is what? A resistor value into the RMS square current flowing through it, or it is V RMS square by R, or you can say it as V RMS into IRMS. These are very simple things, basics, fundamentals, but still afterwards we shouldn't get any confusion. That's why I'm telling these things for clarity. The power absorbed in EMF source or battery, it is E into average current flowing through that EMF source. Power absorbed by the resistor is nothing but the resistance value into the RMS current that is flowing through the R value, R, which is equal to VRMS square by R. These conversions and all, because VRMS equal to IRMS into R in the resistor. So these things we don't discuss in the middle. So just in the starting itself, we have to, if you want, you can refer to our chapter on basics. Exhaustively, all these things are discussed exhaustively. The power electronics requires few fundamentals. Typically, they are not told in a proper way. You take Dimda or the brilliant materials or Muhammad Rashid. They have not devoted any chapter for the basics. That is the problem. These are very fundamentals. So these are not told in a clear way. These basics are not given in single place. These basics are not given in a single place. That is the problem. What we are doing is we are putting one chapter for the basics. So there everything is discussed. Whatever is required, everything is discussed in those basics chapter. So it becomes easy for the student to understand. So you please refer to our chapter on basics. This is very important. Now we will see the waveforms. I am drawing the VS. minus Vm, this is plus Vm, and this is the Vs, the input voltage, Vm into sin omega t. Okay. Now, what I have is I have some EMF in the load. Let it be this value. Okay. Assume initially no current in the load. No current in the load. So I0 is what? 0. There is no current in the load. So what happens? I0 is 0. I0 is 0. What about V0? V0 is E. The drop in resistance is 0 because I0 is 0. So V0 is E. So that's what we have showed. So here the voltage is E and here I am having Vm into sin omega t. Here I am applying Vs equal to Vm into sin omega t, and this side I have E. Now tell me, when this SCR is forward biased, for this SCR to be forward biased, this voltage has to be greater than whatever voltage I have here at the cathode. Here I have E. So the moment when this increases above E, this is forward biased. So the SCR is forward biased in this region and reverse biased in this region. Forward biased in this, reverse biased here. I will use a different mark so that you can easily understand. This is the region where it is reverse biased, and this is the region where forward bias occurs. This is for forward bias. Okay. This is for reverse bias. Reverse bias. Okay. It is forward biased in this portion and in this portion. The SR is forward biased in this region and in this region, and SCR is reverse biased in this region and in this region. Simply, when Vs is greater than E, the SCR is forward biased. The moment when Vs is less than E, it is reverse biased. That's all. So, what is the minimum firing angle? The minimum firing angle is the point where Vm into sin omega t exactly equals to my E. So this is the minimum firing angle. This is the alpha minimum, I say. Okay. What is the maximum firing angle? The maximum firing angle corresponds to this point. Okay. Because I can fire the SR in this point, in this region. So minimum occurs at this point and maximum occurs at this point. Okay. And this is the alpha max. This is the maximum firing angle. So what is the range of firing angle? The range of firing angle is what? Alpha min less than or equal to alpha less than or equal to alpha max. What is alpha min? How do you get? You have to equate Vm into sin omega t equal to E. For getting alpha min, we have to equate Vm into sin omega t equal to E. At this point, omega t is what? Omega t equal to alpha minimum. So this becomes Vm into sin alpha minimum equal to E. So alpha minimum equal to sin inverse E by Vm. Okay. This is the expression. Now this thing we will write it here. What is alpha minimum? Alpha minimum is my sine inverse E by Vm less than or equal to alpha less than or equal to alpha max is what? Pi minus alpha minimum. That you can observe from the waveform. Pi minus alpha minimum. Alpha minimum is what? Sine inverse E by Vm. This is the range of firing angle. So it is between sine inverse E by Vm to pi minus sine inverse E by Vm. Okay. So because of E, what happens? I have some minimum and maximum limits on alpha. Minimum is sine inverse E by Vm and maximum is pi minus sine inverse E by Vm. So let us suppose if I start firing it continuously, then my SCR starts conduction from this point. Okay. Below this alpha minimum, it doesn't start. From alpha minimum only, I can have the conduction. So if I start firing SCR continuously, it starts conduction from this point. Okay. That is the one important observation. Now we will go for the waveforms. Already we have drawn the source waveform. Now we have to draw the V0. That is more important. V0 I am drawing. Also, this one I have to. Here, so many lines are coming. Assume that my firing angle corresponds to this one. My firing angle corresponds to this one. That is what? Alpha. Here I have given the alpha. Now we will see how the output waveform looks. Okay. I have fired at this point, so it starts conduction up to this point. Here, the voltage at the anode, it is what? Becomes E at this point, and cathode, it is E. So here E and here also E at this alpha max point. At alpha max, this corresponds to alpha max. At alpha max, my voltage at the anode is Vm into sine alpha max. It is E, and at the cathode also it is E. So SCR conduction is up to this point only. Beyond this, it is reversible. So SCR conducts up to this point. Okay. After that, what happens? It is off. Again, let us suppose if I fire at alpha in the second half cycle, here I am firing in the second half cycle, then it starts conduction from this point and it goes up to this point. Okay, it goes up to this point. So here my beta is what? Alpha max, that is 5 minus sin inverse E by Vm. Because after alpha max, my voltage at the anode is less than the cathode, so it becomes reverse bias, so it is off. It is off. This is alpha. This is my beta, or I can say alpha max. This is pi. This is 2 pi. This is 2 pi plus alpha. This is 2 pi. Next, this is 3 pi, 4 pi, and so on. When the SCR conducts, I have the V naught as Vs. SCR conducts from alpha to beta. So in that portion, I have the supply voltage. And in the remaining portion, from beta to 2 pi plus alpha, my SCR is off. So what happens? There is no current in the circuit. I0 is 0. The voltage across R is 0. This E appears across this V0. So my V0 is what? Now it is E. It is E. Now I will write the KVL equation. Vs equal to Vt plus V0. Okay. From alpha less than or equal to omega t less than or equal to alpha max. This alpha max is beta. Okay, that equal to beta. Beta. What happens? My SCR conducts. So Vt is 0. Okay. So what happens? V0 equal to Vs. That is what I have represented here. V0 equal to Vs. This portion. Here also V0 equal to Vs. This is also from alpha to beta, but this is in the second cycle. So I say 2 pi plus alpha to 2 pi plus beta. Okay. When alpha max is equal to beta alpha max is less than or equal to omega t less than or equal to 2 pi plus alpha, what happens? The SCR is off. So what happens? My I0 is 0. Voltage across resistor is 0. So V0 equal to what? V0 equal to VR plus E. Since VR is 0, my V0 equal to E. From alpha max, that is beta, to 2 pi plus alpha, I0 is 0. The voltage across R is 0. Whatever voltage is there across E, that appears across the entire load, that is V0. So from beta to 2 pi plus alpha. So this is the my output voltage waveform. Observe, again I am repeating, from alpha to beta it is what? The SCR conducts, so my V0 is Ps. So it is the sine wave. Alpha to beta, 2 pi plus alpha to 2 pi plus beta. The moment when I say my omega t is from alpha max to 2 pi plus alpha, alpha max is beta, beta to 2 pi plus alpha, my tyrist is off, the current is 0. When the current is 0, the voltage across resistance is 0, this voltage appears across P0. So P0 is E. So that's what I have represented. This is E. This waveform is Vm into sin omega t. But this is for only part 2 pi plus alpha to 2 pi plus beta or alpha to beta. Now we will draw the waveform for I0. I0 is very simple. Whenever this SCR is what? Conducting, the I0 flows. Otherwise, I0 is 0. The moment when this is off, what? This is open. Nowhere I0 can flow. So when this is on, then only I0 flows. So what is I0? What is I0? In terms of R, E0. What is I0? I0, this is instantaneous I'm writing. Okay. The I0 is what? V0 instantaneous minus E by R. Okay. So the I0 instantaneous is V0 minus E by R. Even in the graph we can observe the same thing. Whenever this V0 equals to E, okay, this E gets cancelled and I don't have any current in this portion. And whenever V0 is greater than E, here V0 minus P is some positive divided by some current, positive current, meaning the current flows in this direction. So I have the current flowing from only alpha to beta. I0 equal to V0 minus E by R. Okay. Already we have told it flows only when the tyrist is on. Even from the waveforms we can see the same. If you take beta to 2 pi plus alpha, the V0 is E. So V0 is E minus E, 0. By R, it is 0. So from beta to 2 pi plus alpha, the I0 is 0. Beta to 2 pi plus alpha. I0 is 0. It is 0 for alpha max less than or equal to omega t less than or equal to 2 pi plus alpha. And this flows only for alpha less than or equal to omega t less than or equal to alpha max. Okay. The moment when I see this one, alpha to beta interval, at alpha my V0 is suddenly jumping from E to some value, Vm into sin alpha. Here its value is what? Vm into sin alpha. So my current at this instant is what? Vm into sin alpha minus E by R. So the current also will have some jump. Okay. And this is sinusoidal V0 from alpha to beta. This is constant. Sinusoidal minus constant. It is sinusoidal. We can say it is sinusoidal. and you observe at beta. Beta what happens? At beta, V naught is Vm into sin beta. Sin beta is sin alpha max. Vm into sin alpha max is E. So E minus E gets cancelled at beta. So here my current is 0. But here I have some spike. And I have to link it by the sine term. So this is how the waveform of I0 looks. And elsewhere it is 0. Elsewhere it is 0. Elsewhere it is 0. This is the waveform of I0. Actually, magnitude I have put it plus because it is a current. Okay, you can put a suitable magnitude also. Here it is not a sine wave, but here some jump is there and then it comes. Now we want to draw the waveform of Vt. Why we want the waveform of Vt? To know the peak inverse voltage, or to know the commutation time. Okay, to commutation time. So here also now you have to draw the voltage across thyristor. The same thing holds good. What? We apply the KVL. Now two cases. What is that? Alpha less than or equal to omega t less than or equal to alpha max. Here SCR conducts, straight away I get P naught equal to 0. Okay. Now, two cases, alpha less than or equal to omega t less than or equal to alpha max. Okay. Consider alpha less than or equal to omega t less than or equal to alpha max. In this portion, my SCR conducts. When it conducts, PT is 0. Other case is alpha max less than or equal to omega t less than or equal to 2 pi plus alpha. Okay. In this part, it is 0. Okay. This is case 1. In case 2, you see what happens. Here I have V naught equal to E. Okay. Vs is Vm into sin omega t. Vs is Vm into sin omega t. So my Vt is Vs minus V naught. Vs is Vm into sin omega t minus E. You have to draw from alpha max to 2 pi plus alpha. Okay. At alpha max, Vt is Vm into sin alpha max minus E. Okay. Vm into sin alpha max, it is E. E minus E is 0. Okay. Vt is 0 at omega t equal to alpha max. If you put omega t equal to alpha max, I get Vt equal to Vm into sin alpha max minus E. So that value is 0, you have seen earlier. And at omega t equal to alpha, Vt is Vm into sin alpha minus E. Similarly, Vt equal to 0 at omega t equal to alpha min. These two things are important. Now what I have? Vt is 0 at alpha min. Alpha min is what? This point. Alpha min is this point. At this point, voltage across thyristor is 0. And similarly, at alpha max, the voltage across thyristor is 0. Here also in the second cycle, the voltage across the thyristor at 2 pi plus alpha max, it is 0. And similarly, the voltage across the thyristor at 2 pi plus alpha min, it is 0. What I am saying is, the voltage across thyristor is 0 at omega t equal to alpha min or alpha max. This corresponds to alpha min. So I have put the voltage across thyristor as 0. And this corresponds to alpha max. I have put voltage across thyristor 0. And this corresponds to what? Alpha min, 2 pi plus alpha min. I have put the voltage across thyristor 0. This corresponds to 2 pi plus alpha max. I have put the voltage across thyristor 0. The remaining thing I have to draw from alpha max to 2 pi plus alpha. This is the waveform of Vt. Vt is Pm into sin omega t minus E. Okay. When I go beyond alpha max, the voltage across thyristor becomes negative. That's why it is reverse biased. Okay. At omega t equal to alpha max, the voltage across thyristor is 0. When I go beyond alpha max, the voltage across thyristor is negative. And again it is negative at 2 pi plus alpha min. The same thing I have written. These two things, I know these 2 points, it is 0. In between it is negative. So I have connected by the negative waveform. Similarly, the same thing appears. What is this peak value? Peak value is Vm plus E. Because the peak value corresponds when I have here minus Vm. If I have minus Vm here E already I have. So these two add and then I get the reverse voltage, peak reverse voltage. So what I have calculated is peak inverse voltage. That is Vm plus E. Vm plus E. Now I have to calculate the commutation time. How do I get commutation time? I have to get from the Vt waveform. How do I get the commutation time? Commutation time I have to get from the Vt waveform. I have to look at the Vt waveform and then I have to see where exactly my Vt is negative. That corresponds to the commutation interval that I equal to omega Tc. Tc is nothing but that commutation interval divided by omega, so much of seconds. This we have done it for the other cases, and the same analysis holds good even for the RE load. Now we are calculating the commutation time. For commutation time, one has to look at Vt waveform, okay, and also where Vt is becoming negative. Where Vt is becoming negative. Vt is negative from this point to this point to this point. Vt is negative from this point to this point. You look in the graph. What this corresponds to? This corresponds to beta. This corresponds to beta, meaning alpha max. What this point refers to? This point refers to 2 pi plus alpha min. This refers to 2 pi plus alpha min. So my Vt is negative from beta to 2 pi plus alpha min. Vt is negative from beta to 2 pi plus alpha min. Already I have told you beta is alpha max. So Vt is negative from alpha max to 2 pi plus alpha min. But alpha max we have calculated. It is pi minus sin inverse E by Vm, or this value is alpha min. Beta equal to pi minus alpha min. So beta or alpha max, which is equal to pi minus alpha min to 2 pi plus alpha min. So these are the limits of the interval. I have to calculate the time duration. Time duration is this minus this. So I get pi plus 2 into, sorry, this is minimum. Beta is alpha max. Alpha max is what? Pi minus sin inverse E by Vm. Sin inverse E by Vm is my alpha min. So alpha max I am writing as pi minus alpha min to 2 pi plus alpha min. So these are the limits for the interval. So if I want the interval duration, I have to take a difference of these two. That is pi plus 2 into alpha min. This corresponds to my Tc, but this is what? Angle duration, this is time. So to equate the dimensionality, I put omega t, omega Tc, that equal to pi plus 2 into alpha min. So my commutation time Tc is pi plus 2 into alpha min divided by omega, so much seconds. Now we will calculate V0 DC. V0 DC. So for calculating V0 DC, we have to look at the V0 waveform. So you tell me how V0 is. V0 is having two parts. One is V0 equal to Vm into sin omega t from alpha less than or equal to omega t less than or equal to alpha max Okay, and V naught equal to E for alpha max less than or equal to omega t less than or equal to 2 pi plus alpha. Okay, this I have written for a interval of 2 pi, that is the cycle time. So given this specification, anybody can calculate the average V naught value. So now you do the integration. V naught dc equal to what? 1 by 2 pi integral over, you can say 2 pi, integral over 2 pi. See, instead of 0 to 2 pi, I can put alpha to 2 pi plus alpha, because I have written the waveform in that form. I have put the equations in that form. So I expand from alpha to 2 pi plus alpha instead of 0 to 2 pi. V naught into d omega t. Okay. Now you expand 1 by 2 pi integral alpha to alpha max Vm sin omega t. Okay. So this is the V naught value from alpha to alpha max into d omega t plus alpha max to beta, alpha max to 2 pi plus alpha, it is E, V naught is E into d omega t. Now you simplify it. What I get? 1 by 2 pi, it is always outside. So integration of sine minus cos, the limits are from alpha to alpha max, plus the integration of E is what? E is constant. So integration of 1 omega t, the limits are from alpha max to 2 pi plus alpha. Okay. So if I simplify this one, 1 by 2 pi, that is always outside, into Vm into cos alpha minus cos alpha max. Generally we get cos alpha minus cos beta. Here we got cos alpha minus cos alpha max. Since my alpha max is beta, plus E into this is what? 2 pi plus alpha minus alpha max. This is what I have got. Now we will simplify this a bit. So what happens? It becomes 1 by 2 pi Vm into cos alpha minus cos alpha max plus E into what is alpha max? Alpha max is pi minus alpha min. Alpha max is pi minus alpha min. So this pi and pi, this 2 pi and here pi. What I get? Pi plus alpha and this minus or minus. So I get plus alpha min. So this is the expression for V naught DC. Now we will get this expression from the generalized expression. And we will see whether they are equal or not. Now I will write V naught DC. V naught DC is what? 1 by 2 pi Vm into cos alpha minus cos alpha max plus E E into pi plus alpha plus alpha min. This we got through the direct integration. Now we will verify whether we are getting the same or not from the generalized expression. This part, it is as it is for RL load or R load, but when E comes up, we have to modify the generalized expression a bit. That analysis we will do it. The first part is very clear, up to Vm into cos alpha minus cos alpha max. This is like Vm by 2 pi into cos alpha minus cos beta. That is very easy. We have seen it for R load, RL, and RL with freewheeling diode. But for RE load, this term comes. So how to accommodate this E term, that we will see. This expression we have done through the integration. Now we will verify it through the generalized expression. Now we will recall the generalized expression. So the generalized expression is V naught dc equal to n into V max divided by 2 pi into cos alpha plus diode angle minus cos beta. This expression has not taken E into account. Okay, this expression has not taken E into account. So, if E is there in the load, I have to add E term also. That incorporation, that we will do it now. So, how do I add E? Addition of E, it is very simple. It is very simple. When I have the input supply as Vs equal to Vm into sin omega t, I got what? Cos terms. I have taken the sin term, so I got cos term. Okay. But here it is a constant. Constant value. Let us suppose say, assume that this is my output. Okay, this is E, and this is, let us suppose my output V01. Okay, this is T on. This interval is let us suppose T off. Again this is T on, and this is T off, and so on. This is T off. If I want to calculate average value, the average comes to be V01, V01, average equal to E into T on by T, where T is T on plus T off. So that can be written as delta. For this you refer to our chapter on basics. This is very simple thing. I have V01 as my output. Assume that it is having this kind of waveform. For T on I am getting E, and for T off I am getting 0. Again for T on I am getting E, and for T off 0, and the cycle repeats. If I want to calculate average value of this, that is V01 or V01 average equal to E into T on by T. This is direct formula. Of course, you can do the integration. There is nothing great. It is very easy. That you can do it. So it becomes E into delta. So the same funda is applicable here also. The same funda, because E, it is like a constant voltage. Okay, like whatever we have seen here. Okay, here the E is like a constant voltage, like the example we have seen. So here also E into delta we get delta of E, meaning how much time my E is present, Now this I will modify a little bit. To make it more clear. This is what very crude form. This I have to expand. That expansion I will do it. Now you consider the intervals alpha less than or equal to omega t less than or equal to alpha max. Here the SCR is on. Here my SCR is on. So V0 equal to Vm into sin omega t. Okay. And then you consider alpha max less than or equal to omega t less than or equal to 2 pi plus alpha. I have considered one cycle time. Alpha to 2 pi plus alpha, that is 2 pi interval. So it is one cycle time. SCR is off. My SCR is off in this condition. Now V0 is E. This thing we have already discussed. Here, what is delta E? Delta E is nothing but the time period for which E is appearing across the load. That is 2 pi plus alpha minus alpha max divided by 2 pi. Okay. And also here I say delta Vs. Delta Vs is the duty cycle for which the Vs, that is Vm sin omega t, appears across V0. This is appearing for the interval alpha max to alpha. Now you add these two. Here alpha gets cancels and alpha max gets cancels. 2 pi plus 0. How much? 2 pi. So I get delta E plus delta Vs equal to 2 pi by 2 pi, which is equal to 1. So I write delta E as 1 minus delta Vs. Okay. I write delta E as 1 minus delta Vs. This is very simple. I am expanding. Now delta Vs is nothing but the time for which Vs is appearing across the load. What is that? Alpha max minus alpha by 2 pi. This is delta Vs. That value we have to substitute. Now we will again modify this equation. N into V max by 2 pi into now we will take the substitution, that is n equal to 1, diode angle is 0, beta equal to alpha max. So with this what happens? N1 V max divided by 2 pi into cos alpha minus cos beta is alpha max. So this part we have got as usual. Okay, but this part we are interested in. Plus E into 1 minus delta Vs. V minus E into 1 minus delta Vs. So now it becomes V max divided by 2 pi into cos alpha minus cos alpha max. Okay, plus E into what is delta Vs? Delta Vs is nothing but the duration for which V appears across V naught. That is from alpha max to alpha. So alpha max minus alpha. Since this is a duty cycle, we have to take it as a ratio divided by 2 pi. 2 pi. Okay. Divided by 2 pi. What I get here? V max divided by 2 pi into cos alpha minus cos alpha max plus E into these terms we will substitute now. What is alpha max? Alpha max is pi minus alpha min. Pi minus alpha min. So after simplifying this, this 2 pi minus pi, it is pi minus of minus, that is plus alpha min, again minus of minus plus alpha divided by 2 pi. Just see whether we have got the same thing or not. We have got the same thing. This 2 pi is coming here also. The same thing we have got. So from the generalized expression, we can easily derive the average voltage even for the RE load. Okay. In general, it can be derived for any other load, any load. But it is very simple. So the generalized expression has to be understood thoroughly. Now I have to calculate I0 DC. Calculating I0 DC, what I have told you? Recall. How I have calculated I0 DC? Always I get I0 DC from V0 DC. Okay. Always I get I0 DC from V0 DC. First calculate, first obtain V0 DC, and then we calculate the I0 DC. You tell me what is the DC voltage here? The DC voltage here is E. The DC voltage across E is E, that is DC source. Okay? VE DC, voltage across E, but I have taken the average. Okay? The average voltage across it is E. That's all. It is very simple. Because always, it maintains E. So peak value, instantaneous value, RMS value, average value, whatever you take, it is E. So I write the KVL in this equation. What happens? V0 DC equal to what? I0 DC into R. DC value of E is E. Okay. Thereby I0 DC equal to V0 DC minus E by R.